Well, welcome everybody to SAGANet, which stands for Social Action for Grassroots Astrobiology Network. We're broadcasting a special event today, live from the Western Pacific Ocean, from the Joides Resolution Scientific Drilling Vessel. So my name is Julia DeMarinis, and I'm the Education Officer on the Joides Resolution. That's a part of the International Ocean Discovery Program. So normally my home is in Denver, Colorado, but I'm coming to you today from the middle of the, not the middle, but from the Western Pacific Ocean. And it's my great pleasure to be here with you guys. And without further ado, we're gonna start. Just wanna say thank you so much to Sanjoy, who is organizing and being the video jockey for all of this technology, bringing me to you today. I'm going to say hello to the Denver Museum of Nature and Science, who have us up on their screen, and hi to all of friends and family joining us from across the globe. We look forward to interacting with you guys and taking your questions. So as you guys might know, this is a drilling vessel from the slide, and we are drilling rocks at the bottom of the seafloor. And if you're new to this program, you might be wondering why that's important. So I'm an astrobiologist and astronomer in my background, so you might be wondering, what am I doing on a ship in the middle of the ocean? But I really like this expedition because it is dealing with the bigger picture of, is the sound coming through okay? Great. Of what makes Earth special. So I'm going to share with you a couple of photos really quick, so just bear with me. Just take me a second to pull them up. Great. Okay. So, Earth is the only rocky planet that we know of that has two types of crust. We have seafloor crust that basically makes up most of the ocean seafloors, and continental crust, which is what you guys are probably standing on right now. And so Earth is the only one, not Venus, not Mars, not Mercury. And it's very confusing as to why. Even with scientific research, we still are quite confused as to how exactly we can make a continental crust. So the difference between continental crust and seafloor crust is more dense and cold in nature. So when it interacts with a continental crust, it will subduct underneath. Its composition is less silicon than continental crust. So continental crust is on average more andesitic, which, as you can see by this little diagram here, has more silicon in it. So the question is, how do you make continental crust? It's not anywhere on the other planets, but it seems to be unique to Earth. Possibly water is a good reason for how it's made. So there's a couple places on the Earth where continental crust is being formed. One of those is underneath where we are right now. So let me erase this. Oops. And show you exactly where we are. So we are here. This is Japan up here. The red outline is the outline of it's just the outline of Japan. And so all of this is underwater. So you might think that the seafloors are flat, but in fact they're mountainous. And we are looking right now at a boundary between two plate tectonics. Over here is the Pacific plate. I'm going to write PAC for short. Excuse my bad handwriting. The Pacific plate is more or less moving in this general direction. And this is the Philippine plate over here, Phil for short. And so the Pacific plate is subducting underneath the Philippine plate, which is a continental plate. And it is producing a volcanic arc right here. And on our expedition, we have two drilling sites. We drilled here for one of them on what they call the forearc. Then we cruised over here and drilled here on the rear arc. So, and now we had a trouble at this hole, so we had to stop and go back to this hole. So we're drilling over here right now. So we're about 65 kilometers away from our port, which is in Yokohama, which is right near Tokyo. So that's where we are right now. And we were drilling into what I was talking about, the back arc here. So strangely enough, the back arc and the fore arc have different compositions. The back arc is showing seismic data of having more andesite forming underneath it than the fore arc. So that's why we're drilling here, to understand better the history of the volcanoes around us. So if you can see, there are these tiny little ridges here. And these are tiny little underwater chains of volcanoes as well. It might be confusing because I just mentioned that there's one here as well. So hopefully it won't get you too confused, but we're drilling kind of in the saddle between two chains of volcanoes. And we're drilling through a lot of sediment. And the sediment preserves the history of these volcanoes with ash layers. So as we drill down, it's kind of like, almost like tree rings. We're drilling back into the history of this volcanic area by looking at ash layers. So another quick example of what I'm talking about. You can think of this as the Pacific plate subducting underneath the Philippine plate over here. And so the Pacific plate is hydrated. It's a seafloor plate. And the water from the oceans will seep down through pore space or through cracks and hydrate this plate. And as this plate subducts underneath, that plate's going to warm up and that water is going to want to escape. It's going to heat up. And when that water goes upwards, it's going to interact with mantle from over here. And it's going to act kind of like you would sprinkle salt on an icy sidewalk and melt the ice really quickly. So water acts like the salt does to the rock, or excuse me, salt does to the ice, and that it melts rock a lot quicker. So if you want to melt rock, add water to it. It will melt a lot quicker. So when you have rock melting quickly and at lower temperatures, you build up pressure and you create these volcanoes. So that's how most volcanoes are created, at the intersection of these plate boundaries like this. And we can't drill into the volcano, but we're drilling in between two underwater volcanoes, trying to understand the history of these to better understand what is forming below these volcanoes. So that is why we are here, and we are drilling back into time. So this is your standard geologic time scale. We started here. The oldest rocks we got were around 23, maybe in the Miocene. We haven't gotten to the Oligocene, but the rocks are pretty old. So this is the part in the when I broadcast to schools, I like to hear people's thoughts on how they think we can age a rock here on the ship. So if there's any comments from the audience, I know probably the Denver Museum might want to share their thoughts, or if anyone joining in on SAGANet wants to type it in the chat box, Sandra will relay these to me. So I'll give you guys a couple seconds to think about it. Okay. No comments yet. So I'll just explain in my own words how we do it on the ship. We have limited lab space here on the ship. So we don't have all these great radiometric dating tools that you have at some university labs. So how we do it here is a couple ways. One, we look for fossils in the rock layers, tiny little microfossils called forams. And these are basically, you need a microscope to look at them, and they evolve really quickly. And there's a couple that we call index fossils that are alive during a short time period. And if we see them in the microscope, we can age the rock layer based on the fossils that we see. And later on our tour, we're going to show you some of our paleo lab and meet one of the scientists. Another way we can measure time and date the rock is by looking at magnetic field lines. So the Earth goes through magnetic field reversals where our north and south magnetic poles will flip in polarity. And we can see evidence of that by minerals laid down and deposited over time. And they'll be preserved in our rock record. So we have a couple of scientists working on that right now, trying to work out that data. And with our fossil record and our magnetic mineral record, we can put an age to these rocks and tell a better story. So you might be wondering now, how on earth do we get rock up from the seafloor? I'm going to show you in a couple diagrams how we do that.
Question from the Denver Museum. Are there
Yes.
other locations in the world similar to where you're drilling, and what makes where you're drilling special?
Ooh, good question. Okay. Yeah, so there are a couple of other places in the world where we do see continental crust forming, or at least seismic evidence for it. The reason why we are here just south of Japan is that this area is studied extensively seismically. So there's a lot of pre-existing data describing this area. So example, when you're writing a proposal to get an expedition out here funded, you need to have the data supporting it and saying why it's good. So one of the primary reasons we are here is because the data supports it, as well as the ship was actually physically in this part of the world. So if you can imagine, it takes a lot of money for fuel to transit across the world. With a big drilling ship like this, they try and time the proposals that they get based on where they are in the world. Let me just show you guys, I don't think I mentioned this, but this is a picture of our ship. It's 144 meters in diameter, and this derrick here helps us with our drilling. It looks like an oil ship. In fact, it used to be. It was built in the late 70s by BP, so British Petroleum, and they converted it to a scientific drilling ship in the 80s, and the last time it was refurbished with new lab equipment was 2009. So this ship's been around for a while, but the technology is all up to date. Okay. So let me explain how we actually get to the bottom of the seafloor and drill. So here's our ship sitting in the Western Pacific Ocean off the coast of Japan, if you're just tuning in. It is 3:15 in the morning for us, I forgot to mention. So we are a 24-hour operation, and we have shifts. So my shift starts at midnight and ends at noon, and we work 7 days a week. So on the ship, we have a hole at the bottom of our ship called the moon pool, and that's where we send our drilling pipes down. We link our pipes together. They're about 30 meters in length, or about 90 feet, and they string them together kind of like you would a screw. They have threading, we string them together one by one till we hit the bottom of the seafloor, and then we begin our drilling down, and we can bring up lengths of about 10 meters or 30 feet section of rock or sediment at a time. Now, when we bring it back up, we bring it through the same pipe and onto our ship to be analyzed by our scientists in one of our 4 laboratories.
Question from Renee.
Yes.
How many scientists are working on the drilling project?
Great question. So we have about 32 scientists. There's about 130 people on board as we speak. So about 70% of the personnel on the ship are here to support the scientists getting their rocks and supporting the science, which is amazing to think about. And these are expensive missions, so it's a big deal to come out here and do one of these. So as an astronomer and astrobiologist, I had no idea that these sort of expeditions even existed. So this has all been extremely eye-opening, and I'm really excited to share this awesome technology with you guys. Thanks for the question. So when we first drill down, we're getting into sediment. So we've been pulling up, first we pulled up a couple hundred meters of mud. I forgot to mention we are 1.3 miles above the seafloor, or about 2,100 kilometers. So that's how much water we have to send our pipes through. And then the deepest that we were able to drill is 1,800 meters, which is just over a mile. So about 2.5, I'd say, yeah, 2.5 miles total of pipe that we've strung together and drilled down. So it's pretty impressive. The rock got a lot harder. But now we're drilling at our other site, so we're bringing up mainly mud, which we'll show you guys in the lab. Okay, so I really like the movie Life Aquatic with Steve Zissou, and then one of the scenes he says, "Let me tell you about my boat." But I want to see how you think I did here. Pretty good. So without further ado, I think it's time for a tour, unless there are any questions from the audience. Okay, so in order to go on the tour, I have to wear some safety equipment, which I have here. Take off my hat. Sorry. Okay. And put in some earphones because it's loud outside. Can you guys hear me still? Okay. Great. So this is an exciting time for us because we just had last core on deck just about 40 minutes ago. So welcome everybody to the Pacific Ocean at just after 3:15 in the morning, about 3:20 in the morning. I'll put it over here. If your screen has good contrast, you might be able to see some ocean reflecting the ship's lights, just to prove to you we're on the water. So anywhere we go past this line, we have to wear a hard hat. And here is a view of our lovely derrick, which kind of looks like the Eiffel Tower, but a little bit more industrial, maybe a little bit less romantic. All right, so now we're walking up to the core deck. And if there are any questions throughout, just type them in so Sandra can relay them to me. So this is what we've called the catwalk. And this is where core is brought up first. Just get something like it.
2 questions.
So right now they're cleaning the labs because we literally just had our last core on deck. So our expedition is about to be over, sadly. But right now what they're doing is logging. So they're going back down the hole with logging tools, trying to make measurements of the rock surrounding the hole that we just drilled. So this is the rig floor. To put it into perspective, we are right underneath the derrick. And the derrick is awesome. It can hold up to 1 million pounds of weight. So this pipe in the middle, that you can see here, is going through our ship, down through the bottom, through the moon pool and into the ocean. And it is spinning, if you can see. And that's how we core. And in order to get the rock or sediment out, they have to split these open and pull it out with a string. They use this instrument over here that looks like this. It looks kind of like Wally. It's red. This is the iron roughneck, and that helps to string the pipes together one by one and lower it to the seafloor or pull it back up. So I'm just going to give you a panoramic view of where we are. We have our drilling team offshore that's working 24 hours as well. I'm going to take out my earphones so you can hear the rumble. All right. So that's how we drill. So let's go meet the most important tool that we have here on the ship, in my opinion. This is our drill bit. And I'll hold it steady so it can focus really quick. It's made out of metal, and these things rotate under friction. I can't really do it, but if you're strong enough, you can actually turn it with your hands. This is how big it is for scale. And normally, you know, when it's drilling or coring, it's flipped upside down. And this grinds away at the rock, leaving a core intact. And that core, it's cored into these plastic tubes like this, and this is what we call core liner. And so when it's brought up from the seafloor, they yell, core on deck, core on deck. And we literally just had our last core on deck. But then when they bring it up, it's in 10-meter lengths of this core liner here, and it's laid out all the way down there. So once it's laid out, the technicians come and they split it up into smaller sections, as you can see here. And that's so they can handle it much more easily than carrying around a 30-foot section of pipe with rock in it.
Question, Julia.
Yes.
Do you ever lose any of the newly drilled cores as you pull them up from the surface, to the surface?
So the question was, do we ever lose core, right?
Yep.
When we pull it up?
Yep.
Yeah, good question. Sometimes we do. But we don't actually see it. It's not, usually what will happen is the core catcher will be faulty, and it will drop some back into the hole that we'll have to actually core through again. Hopefully that answered your question. Are there any other questions?
You have matching pajamas.
What?
You have matching pajamas to your hat.
Oh, yes. Thank you. I try. Okay, so once the core is brought up, it gets put into these racks inside the lab. So this is the core lab, and there probably are some there, or no, they might have just taken them to be split. So they're put in here to get to room temperature. And now's the time I like to ask, do you think that the core comes up hotter or colder than room temperature? Usually it takes between 1 and 3 hours for it to get to a room temperature. All right. No one seems to be
Denver Museum
willing to,
colder.
brave enough to guess.
Denver Museum.
What does the Denver Museum say?
They think colder.
Colder. Cool. Yeah, so you're right. It's colder mainly because of the seawater around it is really cold. So it takes about 1 to 3 hours to warm up to room temperature. And let's go in the lab to see more about it. So one of my favorite things is walking through these doors here because they're really heavy and you get to spin this wheel. Very nautical. They're watertight just in case we have bad weather. And one of the first people to deal with the core is our friend Sue here. Mm-hmm. And Sue, where are you from and what do you study?
I'm from the UK and studied geology, and now study volcanoes. Very so cool. I'm out here and excited about all the volcanic ash layers.
Cool. So you're one of the first people that gets the core. Can you describe what you do?
So basically we take these cores, one here. So it's basically a drain pipe full of mud, how I find it best to describe. And we measure the physical properties. So that's density, porosity, magnetic susceptibility, which is basically how much iron and things like that are in it, P-wave velocity, all sorts of different properties. And then we use this, take this well out, use all this information to try and help distinguish different units within the overall, however deep we drill, like 100 meters or a kilometer even at the last hole. So here we've got the machines that are running. So this is the whole round multi-sensor track. So there's 3 different instruments, and you just put the core on, let it run, and it does it all automatically.
So it's actually going right now.
Yeah, yeah.
You can see it'll jump at about 5 centimeter increments.
So at where we are at the moment, I'm not sure if Julia said that we've gone back to a previous site, like right where we started from, and we've been drilling extra holes to look for a special ash layer. And so this is some of the physical properties data, and it's a bit like looking at the matrix, but if you can get your eye in down here, you can see that these peaks all line up pretty well.
So this is going down in depth?
Yeah, that's right.
Okay.
So these are the different holes that we've drilled. They're all really close, maybe 20 meters apart, and this is depth. So about 40 meters, they all match up pretty well. And then after that, we see some differences. So we can relay this information to the core describers, and they can then understand what's going on. So they know that there's disturbances due to drilling. Maybe there's been sediments been moved in one place but not in the other. So it's quite important to have these records to sort of integrate all the information. And we've been especially useful recently in finding this special ash layer in what's been termed the magic ash. So here we have some nice curves. So we've got a low signal in one of our properties, the gamma radiation. And we've got a low signal in the magnetic susceptibility, so it's got like low iron. And this, what you see here, is what you're going to see on the sample table in about 2 minutes, I imagine. So it's a really good example of how all the different science going on the ship all fits together really well.
Cool. So you're going to literally publish something that says magic ash?
Not sure. I'm sure someone will try to get that in somewhere. But
Wonderful.
Yeah.
Well, thanks, Sue. And if there are any questions for Sue, please type them in. If not, we will continue our tour.
Question, Julia.
Yes.
How old are the rocks you're studying, and how old is the Earth?
So the rocks that we're studying, they vary in age. I think we're going to talk to the paleontologists in a minute, and they will tell you more about that. So I'm not sure about these. You'll have to ask them. They know all the age questions.
Okay.
We do properties.
What was the second part? How old was the Earth?
Yes.
4.56
Yeah.
billion years?
Yeah.
Awesome. All right. Well, thank you, Sue.
Enjoy.
Another
Right.
question for Sue. Is it felsic ash?
Is it felsic ash? Was the question.
You'll find out in a minute.
All right. Save that question. All right. So we're going now into the core lab. And after Sue runs the core through her machines, the core is brought into here. This is this splitting room or the saw room. Splitting room. This is Lisa, one of our lovely technicians. And she's going to help split this core in half lengthwise. So you can see maybe that there's a black line, and that's how they line up their instruments to slice it in half. When these are sliced in half, one half is called the archive half, which will go into one of 3 repositories over the world. There's one in Texas, in College Station. There's one in Japan, and then there's one in Germany. And I believe all of these cores will go to Japan. And that's dependent on where in the world they are cored from. So the working half gets sampled by the scientists on board. We're going to go look at that in just a second. When are you guys planning on slicing it?
Later,
Sure. Let's just show them. how it works. So it kind of is like this one, because it's sediment, is like a giant, what, cheese slicer?
Yeah, it's a giant cheese cutter.
Cheese cutter. So it's a wire.
Got little blades here to cut through the plastic liner, and then a wire to split the center.
Cool, let's see it in action. Cool. So it goes pretty quickly. We're gonna see, this is the first eyes that we'll have laid on these, on this core. And that's how we split a core. So this is mainly mud, and with some ash layers maybe?
Actually ash, yeah. Go down and back in time.
And back, so this is going back in time this way? Cool. Excellent. Well, thank you, Lisa.
You're welcome.
All right, so this is the core describing room. We have some cores laid out here on these tables, these specialized tables. And the core describers, they stand around and they analyze it and make really fine descriptions of it. And let's go see what they're up to. So this is the core describing team. If you guys want to introduce yourselves and say where you're from.
I'm Abby. I'm from the UK, but I work in Sweden.
I'm Cedric, I'm from France, but I work in Norway.
Hi, I'm Julie. I'm from Germany. Else work there.
I'm Graham. I'm from Britain, but I live in Bakersfield, California.
Very cool. And so what are you guys doing right now? And I'll get to you.
So we are describing the cores. I think you've seen how they get split and everything. And so now we the working parts and the archive parts, and we describe all the different layers within these cores. And we use these toothpicks to define our intervals. And in this core, you see a really nice flat ash layer, which is the product of a volcanic eruption.
So this whole thing is an ash layer?
Yes, well, it's more than 50 centimeters thick. And these white spots, we already took samples for post-truth research, because we really would like to know where this layer comes from and where the process is behind this eruption.
Great, thanks. And so just want to see what your favorite part of being a core describer is.
Getting to work Tuesday and Cedric. And well, maybe after.
All right.
And that's logic.
And the best logic.
So they record all of their information, all the cores that they describe into a program called DeskLogic. Are there any questions for the core describers?
Is it felsic ash?
Oh yeah, is it felsic ash is what they were wanting to know.
This dark one is a mafic ash, but then the lighter color ones, like here, this is a felsic ash. So we see both types interspersed with the mud. So the area has experienced both types of volcanism through the last few 100,000 years.
And how old are those rocks?
So how old are these core samples?
This is approximately 750,000 years.
Cool. Any other questions for the core describers?
Can you tell by texture, or do you have to do chemical analyses of the ash?
Can you tell by texture, or do you have to do chemical analyses?
We definitely have to do a chemical analysis. Some features like this really well sorting is a good indicator that it's the product of a fallout deposit, so of an eruption cloud that traveled through the air. But we definitely have to do chemical analysis to exactly know where it comes from.
Very cool. Well, thanks, guys. We're going to move on to the Paleo Lab. And this is my friend Miriam. Do you want to say where you're from and what you do?
Yeah, I'm Miriam, and I'm from France. I'm a paleomagnetist, and I'm working in Japan.
Cool. So you help date the rock and put an age to it. And by date, I mean, I don't mean take it out to dinner. I mean help tell how far back in time the rocks that we are drilling are. So can you describe what you do here every day?
Yeah, so we measure the sections, so we magnetize them by using this instrument, so the section goes in and out. So this is a cryogenic magnetometer, and we collect also some cubes, like this one. So this one are brown because they are cooked to very high temperature, to 650 degrees.
So let me just pause and explain what we're looking at. So
Yeah,
these are little sections that they've labeled of rock. They bake them to make them. First they chop them into these cubes, and then they bake them, right?
Yeah.
And then they send them through machines to help
exactly.
show the mineral.
Yeah, the magnetic mineralogy and also the polarity, and so we can determine which interval the magnetic field was reverse or normal.
Great. Cool. And are there any questions for Miriam?
How many reversals have you observed?
How many reversals have you observed?
Oh, it's a good question. Many. I think more than 10. Yeah, more than 10. Yeah.
And how far apart are they?
It depends. It depends on the sedimentation rate, and the reversals of the magnetic field are not regular, so it depends. So some interval are many reversal, and for some very long constant polarity.
Excellent. Are there any other questions for Miriam?
Do you think our magnetic
Just
field
to
will
point
shift
out, this
soon?
is a huge machine. It's a cryogenic machine. Very cool. And what was that, Sanjay?
Do you think our current magnetic field will reverse soon?
Do you think our current magnetic field will reverse soon?
Not soon, but it will reverse maybe in thousands years, thousands and thousands of years. But yeah, it will reverse.
All right, cool. But then I won't be watching my compass. All right. Well, thank you, Miriam.
Thank you.
Bye. All right. So welcome everyone to the Paleo Lab. This is the lab with all of the microscopes. And we're going to talk with my good friend Eleanor.
Hello.
And she's going to tell us what she does here on the ship and what do you study?
So I'm here as a micropaleontologist. So my specialist area is looking at microscopic organisms, specifically a group of organisms called foraminifera. And purpose of me being here is to put an age on the rock, much like Miriam, who I believe we just spoke to. And I'll just show you a couple of pictures to explain. So the group of fossils I look at are called foraminifera. They're really abundant in the world's ocean. They live the deepest part of the ocean. They live in estuaries. Some of them float around in the ocean. Some of them live on the seafloor. The ones I'm interested in are ones like this. So they float around in the ocean. They have a calcium carbonate shell. And this one even farms its own algae, which is great. And when they die, all these shells collect on the seafloor. So when we get the rock up from the seafloor and we wash all the mud off, this is the sort of thing we're left with. So these are numerous calcium carbonate tests, is what we call the shells of the foraminifera. And as you can see, there are lots and lots of different shapes and sizes of foraminifera. And the reason we can use these to date the rocks, so put an age on the rocks, is because they evolve really quickly through geological time. So certain species can tell us quite a narrow age range of the rock. So that's my purpose on the boat, and very, very important.
And what did you study in school?
So I did a bachelor's in geology in the UK and a PhD in some sort of weird combination of geology, ocean chemistry, and mass extinction events in the geological record. So, yeah.
Cool. Are there any questions for Eleanor? And studying fossils on a ship.
What is
So
the
just to
oldest
show you
rock?
guys while you type in your questions. What was that?
What is the oldest rock you have dated?
What is the oldest rock we have dated?
On this boat, 12 million years. That's not necessarily the oldest rock we found, because at some point there were no more fossils as we went down course, so we couldn't date the rocks anymore. But yeah, the oldest one we could date was around 12 million years.
Are forams single-celled organisms?
Yes, they are. They're single-celled eukaryotic organisms. So yeah, they're incredibly diverse for a single-celled organism. They're pretty amazing, actually.
Well, I have a question for Eleanor. What advice would you give to young students who would be interested in doing research like this?
Well, I'd encourage them to do it because it's an amazing opportunity to meet lots of interesting people, and geology is one of those subjects that brings together a lot of different topics, whether it's chemistry, whether it's physics, biology, and just the fact that I'm on this boat is just an incredible opportunity that I wouldn't have had I not pursued doing this as a career. So yeah, pick up it.
Great, thanks, Eleanor. So we're gonna continue down the lab here and talk with someone who studies something even smaller than Eleanor. This is Zach, everyone. And Zach, what do you do and where are you from?
All right, I'm from the University of Nebraska in the United States. I'm a PhD student there, and I study a fossil group called calcareous nanofossils. So these are fossils that are a lot smaller than the ones that even Eleanor studies. So just as an example, this is the eye of a needle, and this is a foram right there, something that Eleanor looks at. So you can see that that's very small. Well, on that foram, I put a red circle there. If you follow that red circle down to here, you'll be able to see a little kind of a circular thing down there. And if you zoom in again, that's a nanofossil. So you can see that even though forams are really small, nanos are that much smaller than them. So to look at them, I have to use a really big microscope like this. So I look at the fossils at 1,000 times magnification.
Cool. Well, thanks, Zach.
All right.
And you have to look at this even then in rough seas, right?
Yes, I do.
And do you get seasick?
I haven't been seasick yet, but I've had a lot of headaches from having to look in the microscope when it was moving around a lot.
Are there any questions for Zach and nanofossils?
Do the nanofossils live on the forams?
No, they do not. But sometimes when nanofossils die, forams will make their test, which is basically their shell out of nanofossils. And those are usually agglutinated forams.
Are they?
So do you have a photo of what it looks like?
Yeah. So when nanoplankton, these are single cell organisms, they're plankton. When they're living, they can make these shapes called cocospheres. So it has all of these different plates that connect to each other and make a sphere shape. So when it dies, these plates will fall apart, and that's what we look at. And it can look like things like this in the microscope.
Very cool. Cool. Was there a question for Zach?
What do nanofossils tell you that forams don't?
So the thing with nanofossils is that, one, there are a ton of them. So they're very, very easy to get samples of them, and they're basically everywhere. In addition, you can use some of them to tell how fertile the water is. And then you can also use them to get ages that the forams can't get. For instance, my PhD work, I work in an area where there are no forams. It's just nanofossils. And it's a big chalk interval.
So are nanofossils just a segment, not an entire organism?
Yes. So the living organism is inside of that cocosphere that I showed. Each one of those plates is not an actual organism. It's a piece of the organism. But you can see that they'll have plates that look similar. They're form taxa instead of like genetic taxa.
Very cool. Cool, Zach. So what's one of your favorite things on the ship so far?
I think my favorite thing is just meeting all of the different people. I've been able to meet people from all over the world, and it's just pretty cool. The shift that I work on is a lot of fun.
Yeah, next shift. All right. Well, thanks, Zach.
Thank you.
And we are, I know, getting close to the end of the hour. So I'd like to show you one more lab, and then we'll wrap up. So please feel free to type in your questions. If there are any. I'm just going to take you down.
What do you eat on the boat?
Oh, I want to show you one more thing that always makes. So this is the floor my office is on, and literally makes me laugh every time. So it's a derivative of a French word, I think, that just means before the mast. So we're going to go into the the Geochem Labs, just to take a look. They're pretty much closing up shop at this. Stopped. I wanted to show you of the fancy equipment we have here on the ship, and they can do analyze things like pore water space by using these machines, or they'll squeeze it together and extract all of the pore water out and do a chemistry analysis on that. All right.
Question, Julia.
Yes.
Will the next expedition return to this area?
Great question. Yeah, I forgot to mention that. So we're expedition number 350, and the next two expeditions are 351 and 352, and they will be all drilling within this area. Not exactly in the same location, but this is called the Izu Bonin Marianas Arc, and so they're going to be drilling one near the subduction zone and one kind of farther away. And with the data from all of these three expeditions, it can paint a really good picture of the plate tectonics of this area. Yeah, great question.
And will they do similar science?
I'm not entirely sure. So probably pretty similar. I know each objective is a little bit different for the upcoming missions. I know on the IODP website, there's more information on the scientific prospectus of each expedition. I encourage you guys to check that out if you're interested. And there's definitely education officers on each of these. So if you're interested in doing more of these sessions with your school or museum, there's links on the webpage as well. And that's joidesresolution.org. And I just want to show you one photo of our moon pool. It's really cool. So this is what it looks like this is our re-entry cone that we've lowered. So literally there's a hole at the bottom of the center of our ship, and normally these gates are closed around here, but when it's open, it's really cool. All right, well, if there are no other questions, I think we can end. It's been a great pleasure showing you the ship and connecting with you guys all over the world. The scientists were thrilled to join with you guys, and I hope we answered all of your questions. And if there are any last minute, feel free to type them into SAGANet, and we'll do our best to answer them. So, all right, well, thanks everyone, and see you stateside.